Hello everyone, welcome to another video. Today we're going to explain the most important and the foundational mechanism, reaction mechanism for organic chemistry 2. So the reaction takes is like this. You take a ketone and you react it with some alcohol, some catalytic acid, and then a Dean-Stark method, which essentially means that you take water out of the solution when it forms. Now, don't be intimidated by all of this because I will explain all of that. But notice how we have oxygens. We had a single oxygen double bonded to the carbonyl carbon in the reactant. In the product, we have that carbon, but it's attached to two oxygens, each of which have an ethyl group on them. That ethyl group comes from the fact that in our reagents we used ethanol, which has an ethyl group on that OH. So notice how in the reactant our oxygen has no alkyl groups attached. That doesn't exist. But in the product we do have oxygens with alkyl groups, and where we get those is obviously the ethanol. So at some point the ethanol oxygen has to attach itself to this carbonyl carbon. So the intuitive answer, the first step of this would be that the oxygen of the ethanol attacks the carbonyl carbon. However, there's a problem with this. Ethanol is a neutrally charged nucleophile, and this ketone is a neutrally charged electrophile. A weak nucleophile and a weak electrophile are not very attracted to each other. And ketones are generally less reactive than things like carboxylic acid derivatives. So we need to make this ketone a better electrophile. We need to make it more positively charged. And we have a lot of acid in the solution, so we can just protonate it. So our acid source, or our proton source, is probably going to be protonated alcohol. So this is what I'm drawing as ethanol with an extra proton on it, extra hydrogen. So we are going to react the ketone with that, and the mechanism is going to look like this. So this doesn't happen, but the electrons on the ketone oxygen come in, attack the proton of the protonated alcohol, and then now the ketone is protonated. So now it's a very good nucleophile. Now ethanol can come in and very easily attack it. And every time we attack a carbonyl carbon like this, one of the pi bonds of, well, basically two of the pi bonds in the double bond between oxygen and carbon go up to the oxygen, because you can't have 5 bonds on a carbon. So as a result, we get the OH is now single bonded, not double bonded anymore. And notice how the oxygen of the ethanol attached itself to this carbon. So there would be an oxygen, and then there was an ethyl attached to that. So there's an ethyl group, and then there's the hydrogen attached to the oxygen. And we have 3 things attached to the oxygen, so it's a positively charged oxygen. Now, notice what's going on. In the reactant, we had an oxygen that had no alkyl group. But in the product, we have oxygens that do have alkyl groups, right? They have ethyl groups. In this intermediate, we have exactly that. We have actually both. We have an oxygen with no ethyls, but we have an oxygen with an ethyl. Our goal should be to keep this oxygen on the molecule and kick this one out. So I'm going to call this oxygen with an ethyl group the staying oxygen, because it has to stay for us to make the product. And this oxygen has to leave because it has no alkyl groups. There's no oxygen without an alkyl in the product. So this is the leaving oxygen. Now, after you basically attack the carbonyl carbon, what the molecule wants to do is reform the carbonyl, because the carbonyl was very stable. So intuitively you might think, okay, well, it would reform the carbonyl like this, so to keep this oxygen on it and then kick the leaving oxygen out. The problem with that is that if you do that, you get something like this. And this is oxygen with 4 bonds, which would be a positive 2 charge, and that's a no-no. And you'd also get hydroxide, and that is a similar no-no. So we don't want to do that. Instead, what we want to do is, because we are in acidic conditions, we have a lot of hydrogen protons. So we have the luxury of being able to protonate the leaving oxygen to make it a better leaving group. If I were to theoretically protonate this leaving oxygen, if it leaves, it becomes water, which is a lot more stable than negatively charged hydroxide. However, if I protonate it, you see the problem. We have 2 positive charges on a single molecule. So first I need to deprotonate the staying oxygen, then protonate the leaving oxygen, and then kick out the leaving oxygen and reform the carbonyl by the staying oxygen. So let's do all of that. So let's go ahead and deprotonate. So deprotonation happens using the alcohol you're doing the reaction with. So I was drawing the arrows orange, so let's just keep that consistent. We want to use a protonated alcohol again. Okay, so now we have done what we wanted to. We have protonated the leaving oxygen, and we have deprotonated the staying oxygen, so that when the staying oxygen attacks, not attacks, but basically reforms the carbonyl like this, and the leaving oxygen leaves, the leaving oxygen is water, which is stable, and the staying oxygen only has a +1 charge as a result, not a +2 charge. The leaving group is water. Now I'm going to take this down and explain something important. I drew the arrow as a straight arrow, however, all of these really are equilibrium arrows. They don't matter in the other ones, really. For this one, they do. Remember in the reaction, when I wrote it, I put Dean Stark, which meant taking out water from the reaction when, as water forms. Now, try and guess why we would do that. Just take a minute and see why it's important to take water out of the solution as it forms. So let me explain that. If you take water out of the solution as it forms, you're decreasing its concentration. And in an equilibrium process, if you decrease something on the left side, the reaction will shift toward that side to try to compensate for the decreasing water. So we're essentially pushing the reaction toward the product by doing that. So now that we have that understanding, the water is really irrelevant. What's important is this. So, I mean, it's relevant that we have to take it out, but we're not doing anything with it after that. So again, our ketone here has a positive charge like it did here, so it's a good electrophile, and a neutrally charged nucleophile like an ethanol can easily attack it. So we attack it and we get those electrons up on that oxygen. Now notice how the one that attacks has a hydrogen on it, so we still have this proton, and then at the end we just need to deprotonate this guy. And we have formed the product that we predicted we would form. Okay, so now it looks really bad, I know it does, but look, There are a few important principles with this. If you understand those, it will make the rest of the course a lot more, easier to predict and understand. So principle number one is that basically a neutrally charged nucleophile cannot usually attack a neutrally charged electrophile. That's with ketones, if ketone is the electrophile. Sometimes acid halides are reactive enough and acid anhydrides are reactive enough. But ketones, aldehydes, amides, carboxylic acids, those things, you need to have catalytic acid to be able to protonate them, make them very good electrophiles, and then attack with the neutrally charged nucleophile. So that's principle number one. Principle number two is that we want to keep the staying oxygen on the molecule and get rid of the leaving oxygen. When we have the luxury of having a lot of hydrogen protons in the solution like we do with acidic conditions, we want to get rid of the leaving oxygen while it is protonated, while it is positively one charged. So we want it to be water. But if we want the leaving oxygen to be positively one charged, we can't have the staying oxygen be positively one charged, because that would be a positive two charge on one molecule. That would be very unstable. So the first step would be to deprotonate the staying oxygen, so make it into this, and then protonate the leaving oxygen as we do here, and then reform the carbonyl using the staying oxygen, kicking out the leaving oxygen. Okay. Then again, the same principle here is that a positively charged electrophile is good enough to be attacked by a neutral nucleophile, and you attack again and you deprotonate. Okay. This pattern will come up time and time again. And so now that we understand that mechanism, let's just briefly, I'm not going to talk about mechanisms anymore, but let's go over a few more relevant reactions similar to it. Let's say we have the same ketone and I react it with ethylene glycol. So our alcohol here, instead of being ethanol, is this. All right. And we use the same things. We use catalytic acid and we use Dean Stark. Same exact mechanism. However, the product will be a little weird. So we still, let me actually pull up, actually it doesn't matter. So notice how this forms, right? Basically, the two alcohols that we use to attack the carbonyl carbon are in the same molecule. They're both here. And they're separated by two carbons, which is why we have two carbons here. So essentially, it's kind of like the other one, but these two carbon chains are connected to each other. Instead of attacking with two alcohol molecules, we attack with one molecule with two alcohol groups on it. And we can form that. Now, this has some utility in some synthesis problems. So let's say that you've probably seen this from Orgo 1. You might remember it. That's a bit big. Let me make it smaller. Let's say you have a ketone, but you also have, let's say, like a carboxylic acid next to it. And you want to reduce it so that the carboxylic acid becomes a hydroxyl, so it becomes completely reduced, but the ketone stays the same. Now, if you use lithium aluminum hydride as your reducing agent, it will reduce both of those. So how do you make it so the ketone stays? Well, you probably remember a thing called protection. First, you react it with ethylene glycol and, 1 minute, my pen is being weird. Okay. And with acid and with Dean Stark, taking water out when it forms. And this only does it to ketones and not carboxylic acids. That's another important thing. So the carboxylic acid would stay where it was, but the ketone would turn into this weird thing. Looks like a little thing that has a cap on it. Then you use lithium aluminum hydride and it wouldn't touch this guy, but it would touch and completely reduce the carboxylic acid. All right. Then to reform the ketone, it's very important to understand that the acid is simply a catalyst, so it speeds up the reaction. It has nothing to do with the equilibrium. So we still need catalytic acid. However, Dean Stark was taking water out of the solution as it forms. Here we want to do the opposite. We actually want to introduce water into the solution. The reason is this. So let's go back and let's explain this step again, or actually this step. If you want to go toward this direction, you want the two oxygens with alkyl groups, you're going to have to take water out so that the reaction shifts to the left. What we're doing here is effectively the opposite of that. We want to take this weird thingamajiggery and get the ketone back. So we're going in the opposite direction. So instead what we want to do, we actually want to increase water, put water in, so that the reaction proceeds in the other direction. So that's effectively what we do here. We add water. And the acid is just catalyst, so it won't affect equilibrium. It'll affect the speed at which you reach equilibrium. It makes it reach equilibrium faster. So that's the utility of this reaction. You may be looking at this weird thing going, what was the purpose of this, right? So it's better as an intermediate like that. And of course, that would mean that our steps are, you'd first add ethylene glycol with catalytic acid and the Dean Stark method, and then second step, you add your reducing agent, strong reducing agent, and then third step, you'd add the acid again, but this time with water to shift equilibrium in the opposite direction. So now that we've gone over that, let's explain one more thing briefly. I don't want to take too long. Basically, this same process can occur with aldehydes. So you can do this. Let's use methanol this time. I just want to show one reaction. So try and predict the product of this. I think it's good practice. Okay, so let me show it. It'll be so notice how we had really two carbons here, and so we have those two carbons, but then now the double bond oxygen is gone, and we have two oxygens with methyls because we had a methyl. It was methanol. So now this same exact type of reaction can also occur if you replace the oxygen with a sulfur, and it's the exact same mechanism. I'm not going to draw it again, of course. It's the exact same thing, exact same steps, exact same catalyst, exact same method. But let's say we take let me make sulfur this so that you can appreciate it. All right, if you use sulfur, try and predict the product. I guess I'm drawing it, so I guess don't. So we have 3 carbons attached to that sulfur. So 1, 2, 3, 1, 2, 3. Okay. And of course, you can use the same ethylene glycol version of sulfur. So you can go sulfur, sulfur, and then put 2 carbons between it and react it with any ketone. Let's make it a weird ketone this time. So now you will have like that. The only utility of this, besides the fact that it's not an oxygen is that if you take this guy and you react it with something called Ranley's nickel, it will get rid of that whole thing and you get an alkane. So that whole thingamajigger is gone. Alright? And you get an alkane. So, yeah, that should explain how we use oxygen nucleophiles and sulfur nucleophiles to attack aldehydes and ketones. And you will see that the same principles come up in many other reactions. Of course, it's modified a little bit, but I hope you can, again, understand the patterns that we saw in this reaction and the things that I explained. So try on your own to basically go through some of the examples we did. So like, let's say this one, and maybe even the sulfur ones if you want, and perhaps maybe this one, and try to draw the mechanism and think of the principles that we discussed over here to do it. So thank you for watching, and I will see you in another video.